we'll have McGinley from Cambridge that will talk about, oh, got data, sorry.
We've got
okay, yeah. And he will talk about measuring many properties of a quantum state in an analog quantum simulation.
okay,
Thanks.
super. Thank you very much to Bruno for inviting me to give this talk. It's a real pleasure to be here, and thank you all for coming. So yes, I'm Max McGinley. I'm a recently finished a postdoc at Oxford University, where I did the work I'm going to talk about today with Michele Fava, who's just finished his PhD, he's now at ENS, and Shana Bisnas, who's just moved to Würzburg. And today, yes, the title of my talk is Measuring Many Properties of a Quantum State on an Analog Quantum Simulator. And so just to give a sort of quick, okay, now this has stopped working. This line clicker. Do we need to click on this? And then, okay, we're back. Sorry. Good. So an outline of what I'm going to talk about today. First of all, I'll talk about the motivation. What do I mean when I say an analog quantum simulator? And then there'll be a little bit of theoretical background. And I'm going to introduce two topics, so-called classical shadows and deep thermalization, both of which have very dramatic sounding names, but I'll try and make them sound as easy to understand as possible. And then what I'm going to do is introduce a protocol which has some potential uses in these analog quantum simulators as a form of sort of tomography. And on the flip side, there will be some interesting non-equilibrium dynamics that kind of goes into understanding why this protocol works. So I think there's a bit of something for everyone. And then I'll end with some conclusions and outlook. If at any point I'm saying something unclear, feel free to butt in with a question. Very happy to take them in the talk. Okay, so motivation. We're talking about, in general, we've seen great advances in quantum systems where we have control over the interactions that happen in them. Of course, the field of quantum computing is exactly part of this recent advances. And if you just look at one of these very fancy quantum computers built by IBM, we see some sort of complicated devices, but there's sort of many individual elements, and we can manipulate them individually, have direct control over them, and control how they interact with one another. And the reason we want to spend so much effort doing this is because there are certain computational tasks that we believe are very hard for classical computers, but very easier for quantum computers. And the one I like to think about today is quantum simulation. So we use our quantum device to study and learn something about a different system of interest. Okay. And the usual paradigm is that basically we want to build a quantum computer that can kind of do any quantum task. And so we have this sort of gate-based model where we say basically any interaction between two qubits we can realize and just compile whatever circuit we like. Obviously, such a device would be lovely to have, but there are current limitations in terms of the current sizes that we have, and indeed the noise that these devices suffer from. So analog quantum simulators kind of offer a slight remedy to this, and that these are kind of more specialized devices. They're not built to simulate, to compute any possible task we give them, but instead they can kind of simulate very particular kinds of systems. And so as examples I have in mind, we have ultracold atoms in optical lattices, trapped ions, Rydberg atoms, even some of the QED systems that I showed earlier can be built in a way that they don't have sort of full control, but sort of engineer more broad properties. So what I'm thinking about is that we maybe have some sort of global control over what kind of interactions are. We could engineer some kind of interesting Hamiltonian rather than go in and sort of program individual gates. So when we look at what the kind of time evolution picture of the two on the left, I have something that kind of pictorially represents what we would send to a quantum computer, which is fully programmable. It's all gate-based. We kind of address a few qubits at a time. In an analog quantum simulator, we just turn on some Hamiltonian, and that Hamiltonian is something we're interested in and we want to study it. So this is what I mean by global control. I'll refer to that quite a few times. And the advantage is that we can actually reach kind of bigger system sizes using these platforms at the moment. And indeed, they're very well tailored to quantum simulation as a particular problem. Good. So what does a typical experiment look like when we do quantum simulation? Well, normally we prepare some state of interest. This might be through time evolution, or we might want to cool into the ground state of some interesting Hamiltonian. But just making that state in the first place is all very well. We need to learn something about it, right? We need to measure it. And how do we actually do this? Well, typically there will be some sort of detecting device. And in general, there will be some sort of favored basis that we measure it. So what I've got here is from this experimental paper here of a cold atom gas where they have a atomic gas microscope. So they can image the positions of all these atoms, and you can see sort of even thin resolution is possible. You can see on the left panel something that looks a bit like a hot insulator. So this is very nice. We have some special operators, occupation, maybe spin. We can measure correlation functions just through sort of taking images of this. So that's a good start, right? But there's a slight difficulty, right, in that often we are interested in, well, basically any expectation value, not just these privileged ones. And in particular, anything that's off diagonal in this computational basis, i.e. the basis that we measure directly in, it's going to be hard to get in these systems. In addition, maybe we want to measure like many different observables, but we don't want to have to go into the experiment, rerun a new experiment every time we want to sort of measure something new. That seems sort of a bit wasteful. And actually, there are more general kind of, in the sort of age of quantum information, we're now more interested in some slightly more exotic properties, for example, say Renyi entropies. These aren't just like some expectation value, we need to work a little harder to get some of these. And what I would like to show you in this work is that our protocol kind of addresses these problems. We can measure any observable we want. We can measure many observables simultaneously, i.e. from a single set of experimental data. We can get lots of different expectation values. And even we can get things more sophisticated like Renyi entropies, etc. And the key thing is, I say, we can do this not just in principle, but we can actually do this without asking for a ridiculous number of experimental repetitions. That's going to be the key to the sort of success of this protocol. Okay, so that's my motivation. That's what I'm trying to achieve in this talk. Are there any questions at this point? Yes.
So just,
yeah.
like you said, not just expectation value, but in individual experiments, we tend not to measure expectation value, but an expectation value is an average over experimental run.
Absolutely.
So which are we doing?
Yes, so we're always doing many experimental runs, and the kind of subtlety is in how we process that data. So we get lots of different sort of measurement outcomes, and like you say, the expectation value, summing up all those quantities that we get from each repetition. That's also going to be true in this case. I hope that clears that up. Yes.
So just to clarify, when you talk about this kind of analog quantum computers,
yes,
it's something like, say, for example, if I wanted to, I don't know, calculate the expectation value of something in the programmable, instead of putting that with matrices, I would get, say, for example, wedge an atom in a superconducting cavity because that has the same Hamiltonian parameter.
Yes, yeah, exactly. The sort of target is the Hamiltonian, and maybe you want to pick your system that kind of mimics that Hamiltonian if possible.
Right.
That's the thing. Great. Okay, so there's going to be some theoretical background that I'm going to need to introduce, and that will lead on nicely then to introducing our protocol. So the first bit of background I want to introduce is this newly proposed idea called classical shadow tomography. The original reference is up there. And the idea is that this is a protocol that can kind of tick all those ticks that I showed you before. But what it's asking for is that we have a device where basically any gate can be realized. So this is kind of the easy version, right? If we can do anything, then this is possible. And I'll just give you a quick run through how it works. So the idea is that we have some density matrix, say rho target that we're trying to measure. And the idea is pick a unitary at random, rotate into that basis, and then measure in that basis. Okay, and we measure in the computational basis, which I'm always going to refer to as M. So we get some outcome, which is a computational basis state, and we've also picked a random unitary. So the data associated with one experiment is a unitary and a measurement outcome, right? Now, what this team from the group of John Prescott suggests is, once we get that data, let's take a classical computer and just store some representation of this state, this rotated state. So it's U dagger M. In other words, we've kind of undone the unitary that we applied on the quantum device, we kind of reverse it in the classical device. So store that on a classical computer and then repeat many times. And so what we have here are these row I, where I sort of goes from 1 to the number of repetitions that you're prepared to do. And the idea is each of these row I is a kind of snapshot of your quantum state. And that's a kind of analogy for what it looks like, but let's be a bit more specific. So row I is the rotated computational basis states. What we have to do is find some clever function f of a, and we choose that function such that when we input those snapshots, on average, this blackboard E there means an expectation value. On average, what we get is the observable that we're looking for, which is just given by trace of row A. There's some technical details about how one finds this function, but the point is that you can find it and it takes quite a simple form. And you increase your number of repetitions until you get a very good estimate for what you're doing. So there's, on the one hand, we're doing some quantum rotations. On the other hand, we're manipulating our data classically, and out comes what we're looking for. But the point is, as I've kind of tried to highlight with this equation here, the only time when the actual observable we're looking for comes into it is when we choose this function f of a. Right. So the advantage here is that when we do the experiment, we might not even know what observable we're trying to measure. Someone might tell us later, oh, now can you compute for me the expectation value of the spin X operator, for example? And you can do that, right? You have the chance to compute many different expectation values from one set of experimental data. And that's what was really trying to, that's what was brought out in this paper as a real advantage. So it's kind of neat. And the other thing you can do is, I didn't mention, you can compute these nonlinear observables. Because you have a representation of your state on a classical computer, you can do what you want to it, basically. You can square it. You couldn't square a quantum state on a quantum device, right? So, like I say, there are technical details to do with how you choose that function, how many repetitions needed, and I'm going to sort of sweep that under the carpet for now. There'll be a sort of equivalent question when it comes to our protocol, and hopefully that will make it clear how it all works. Good. So that's classical shallow tomography. Any questions there? Yes.
Not a question, but can you show the previous slide for a few more seconds?
Yes.
I didn't quite get how precisely M is obtained.
So yeah, so first you rotate, you do this unitary rotation, then you just do a measurement in the computational basis.
Oh, a measurement in the computational basis, and then you get
and then yes,
M, and that is what you store.
Yeah, exactly. And you get a different M for each experiment. You also pick a different random unitary for each experiment. That's the other thing to bear in mind.
So I also store U on the computer.
Yes.
And that might be quite big.
Well, you don't necessarily, so the trick is you don't need to store the full matrix necessarily, right? Because, well, you chose the random unitary from some set of allowed random unitaries. So actually all you would need to store is like index, which unitary did I pick? I picked unitary number 23. And I implemented that by doing some pulse here and some gate here. This is the idea. There is a separate question about the classical computational cost of all this, which we want to bound. That's the point. And I'll get to that probably at the end. Yes.
Doesn't that depend on the distribution of the unitaries?
Sorry?
So doesn't that depend? It depends on the distribution of
it does. At the end, they advocate for choosing Clifford unitaries. So you choose a random Clifford unitary, which you have an efficient representation for. Yes, but I mean, that's one choice. You can actually, you know, depending on which distribution of unitaries you're prepared to implement, you might say also, let's just choose only single qubit unitaries. And that's another choice. And those are also easy to store. They're just 2 by 2. Yes.
So I guess you're going to tell us whether this is an unbiased estimator or how the statistical error goes.
Absolutely, yes. So I mean, this equation here tells you this is an unbiased estimator because each individual shot on average gives you the right answer, is unbiased.
But there will be some conditions on the air
Yes.
for this to be true.
Yes, absolutely. So yeah, and it's depending on the observable you're looking for. So maybe one of the principles I should say is that there are certain observables that will take very, very many experimental measurements to do. The kind of idea of classical shallow tomography is that there are certain quite useful expectation values that are actually quite easy to get. You don't need very many. You want to keep that scalable, absolutely. Good. All right. So moving on. Another thing, I apologize that the background section of this talk is a little long, but I wanted to get us all on the same page before we start sort of delving in. Okay, quantum state designs is another related topic, actually. And the idea of the quantum state design that we have whenever we have a system and there are some basic states of this complex C to the D, there's a privileged probability distribution over this state, which is sort of maximally random. So the idea of a maximally random distribution of states, we call that the Haar measure. It's some probability density given formally here. Right. The idea is that when we have a quantum state design is a discrete probability, it doesn't have to be discrete, it's easier to think of it as discrete. A discrete probability distribution where we have some probabilities pi associated with each state phi I. And the idea is that their sort of low order moments up to kth order agree with the Haar distribution. So this is a little bit formal. What I mean is that we're taking some average with respect to this discrete probability distribution of states, and it's matching the Haar as long as f is a kth order polynomial. It's a little bit formal, so just by means of example. For example, a one design just simply means that every expectation value agrees with the Haar ensemble. A two design simply means that these products of pairs agree. And by this overline, I mean the sort of average over this distribution of states. Again, maybe this is a little formal, so I think it's nicer to view it a little bit more visually. But there's a very simple example where we just have a single qubit. What do quantum state designs look like? And here we have the block sphere to help us just like visualize this geometrically. So if we have only two states, 0 and 1, then a one design is, for example, just an equal, a 50-50 choice between 0 and 1. That's one design. We could actually choose any two opposing poles on the sphere. It doesn't have to be 0 and 1, but this is just an example of one design. A two design, for example, one example looks like this with a qubit. And the reason this is a tetrahedron is, if you like, you could think about these. If these were masses on a sphere, this would have an isotropic moment of inertia, i.e. the second moments of these kind of vectors are isotropic, and they agree with the sort of maximally random case where we just completely uniformly cover the sphere. And as you can see, the higher k we go, the more arrows we need to kind of keep matching the Haar distribution up to some k, some finite value k. This is for states. There's a similar construction. You can have so-called unitary designs, which is where you're trying to make maximally random unitary matrices rather than maximally random quantum states. That's just thought I should flag that because it will come up a bit. Is that clear so far for everyone? Any questions? Yes.
Potentially done one, but is it true that for all possible quantum systems, essentially the k equals infinity case is the Haar case, or is there ones where they still are divergent?
I think so. There's probably some subtleties about exactly how one takes that limit. But yes, I mean, to have infinite order moments agree with the Haar distribution, you need necessarily a continuous distribution rather than a discrete distribution. So yes, I think that's how we should think about it. Yeah, which I'm not prepared to discuss. Yeah. Any other questions? Great. So why should we care about quantum state designs is the question. Well, one thing you might say is like, well, where do they show up? Well, obviously we can kind of engineer them. I could just tell my quantum computer to make these states, right? But without engineering them, do they arise kind of naturally in any context? And this has kind of triggered an interest in so-called deep thermalization. It's not my term, I don't really like it, but the idea in deep thermalization is to consider this experiment, where one has some many-body state psi. One measures most of the qubits in psi, and what we're left with, so most of the qubits being B here, so we measure everything in B, and we're left with some state on A. Right. And what this gives us is is actually kind of what we're looking for. It gives us a probability distribution of quantum states on A. So there's some probabilities according to Born's rule for which outcome we found on B. And if we do find an outcome, then we know what the sort of conditional state on A is. So that gives us this probabilities and these states, PM phi. And the idea is actually it's surprisingly generic that we find many body states. For many body states, we find approximate quantum state designs when we do this protocol. So from this distribution, we actually see this kind of maximal randomness property. It's called deep thermalization because it kind of goes beyond the ETH hypothesis, kind of an extension of random matrix theory, I think is what these authors up there are trying to say. But I mean, the point is that we expect for complex quantum many-body states, they kind of show maximal randomness when we look at sort of subsystems, and this is the kind of manifestation of that principle. So that's deep thermalization, and it's an emergent quantum state design because we didn't ask the system to do this for us; it just did it itself.
Question?
Yes.
Well, my question is, what's K?
Oh yes, okay, sorry, absolutely. K. So this is up to some K of order 1. If you let K scale with the size of the system, I don't know exactly what happens, but you know, these are there are some rigorous proofs for when this happens. A lot of the time it's just sort of numerical observation. So K is 2, 3, or 4 or something. And we just try and make the system as big as possible. And this is an asymptotic state.
But the dimensions of A and B don't matter.
I think B has to be a lot bigger than A.
Okay. And for a low K, you get a very good approximation of the state.
Yeah. Yeah, there's at some point it's going to be a formula that comes to show some of the scaling. And you know, it also depends how much error you're prepared to tolerate, etc. Yes.
I guess I'm a little confused by your connection with random matrix theory, because there it's formally just a statement on eigenvalues, as I understand it, and it's not a hard measure. It's a distribution that is like has this additional exponential factor depending on what symmetry you have.
Yes. Okay. So I mean, traditional random matrix theory, when we're thinking about eigenvalues and vectors of a chaotic Hamiltonian, then one is not interested necessarily in a collection of unitaries. Well. Okay, I mean, if you look at the eigenstates of a chaotic Hamiltonian, they look effectively random, right, if you're at sort of high enough energy. Or, for example, if you consider a system without energy conservation, if you consider like a Floquet system, consider eigenstates of the Floquet operator, these are precisely the kind of maximally random states that you find. I more meant that as a loose analogy rather than a formal statement. But yes, I see what you mean. Okay. So just to recap, I've talked a little bit about what analog quantum simulators are, why we're interested in them. I've introduced this idea of classical shadow tomography, which is a protocol which we would kind of like to implement if we could, but it has this demand that we have to be able to implement sort of 2-qubit, 1-qubit gates, site-selective gates. And then I introduced state designs, which is where and showed that they can show up in an emergent way in many-body quantum systems. And just as sort of a little foreshadowing, the reason I need to introduce these topics is that emergent quantum state designs will be actually related to that kind of magic distribution of unitaries that we wanted to choose in classical shadow tomography. That will make that more precise. So I'm about to start introducing our protocol. Questions? Okay, Good. So what do we do? Well, as a reminder, we only have global control over our interesting system. And so limited freedom to choose our unitaries. But what I suggest is we do what this circuit represents here. So let's unpick this. What we have is some density matrix we're interested in, that's our state. And what we have here is a bunch of kind of ancillas that we could reliably prepare in some zero state somewhere else in the system. And once we're ready to measure this state, what I want us to do is take this big global unitary and apply it to all the system and the ancillars. I've drawn two system qubits here, but I'm generally thinking arbitrary many NS, system qubits, and NA ancillar qubits. So we entangle them all together, and then we measure everything in the computation basis. Simple. And if I compare it to the shadows protocol, for example, the shadows didn't have any ancillars in, so it kind of looks like this. And if we kind of compare the two, so in the shadows protocol, that unitary UI is randomly picked. It's compiled from gates. It's probably inhomogeneous, but it almost always is inhomogeneous. So that we can't implement that. So this is going to be sort of the cure. This U is that we only need to choose one U, and that's going to actually sort us out. And it can be native to the device. We're not asking for special kind of unitaries. Okay, so now I have to convince you that this does what it says in the tip. So how do we determine these properties of the system density matrix from the measurement outcome? So what I claim is that if U is chosen generically, we break enough conservation rules, etc., then any property of rho s can be reconstructed from some subset of measurement outcomes. So we repeat this experiment many times. Each time we get a different set of measurement outcomes. If we do this m rep times, then I claim we can reconstruct that property using the same number of m rep as in classical shadow tomography. And that number has been characterized in previous works. I'm just trying to sort of match them using fewer resources. So how are we going to show this? Well, the first step is to think about what determines the outcome probabilities in this setup. And okay, it's a few equations, but what you can write, so this here is the probability of getting outcome m if we fed in the target state rho s. And it's just given by this. And here the phi m's are these unnormalized wave functions, this is kind of a partial inward product. So we take the measurement outcome state m, we evolve backwards, and then we just sort of take the inner product with the zero state on these ancillars. It doesn't have to be zero, just as long as we know what it is. And that gives us, what we're left with is a wave function on the system. And we take, and that phi m lets us determine these probabilities. So these are unnormalized. And these are going to play a really central role in what I'm talking about. Yes?
No, an obvious statement. What you're building here is a quantum channel for rho s.
Yes, you absolutely are. And I guess in some sense, the channel takes a quantum state S probabilities.
Yeah.
Indeed. And I thought about formulating it that way, and I kind of flagged that, oh, you can actually formally define this as a POVM, and POVMs have channels associated with them, but I'll try and keep it jargon free. Good. And the key is going to be in what do we do with these measurement outcomes? So there's going to be some sort of post-processing we need to do. So we perform the experiment, we get an outcome. And now I'm going to take a leaf out of the classical shadow tomography book. Let's say we get the outcome. Then let's store this state here. I'm going to normalize it. These tildes will mean normalized states. And just as a reminder, that's what the phi m's are. Okay, so we can do that, fine. And we repeat many times, and let's get some kind of rho estimate. I'm not saying, I haven't yet proved what this rho estimate looks like, I'm just saying, let's do it. And we can see what happens on average, right? If we repeated this an infinite number of times, we would converge to a operator. What does that operator look like? Well, it's a little involved, right? But basically here, what we have is the outcome probabilities. This is basically the same as what I showed in the last slide at the bottom here. I've just kind of factored out a normalization factor, which is Qn. Oops, sorry. And there's the state on the right. So that's just taking the mean. Good. So just flagging this equation here. If we do this, I've put this in a fairly suggestive form with this normalization factor here. And in particular, I want us to focus on these QMs. I've kind of divided appropriately, but the point is that these QMs sum to 1 and they're positive. So let's interpret QM as a probability and tilde M as a normalized state associated with that problem. Yes.
I'm very confused about notation. You have system, you have what I'd like to call environment or the zeros.
Yeah.
Yeah. So this state phi is everything or is just the system?
So it's just on the system, and the point is that we've kind of projected out the ancillas with this 0 state.
Got it.
So yeah, this is full system. This lives on the ancillas. So what's left when we take the inner product is just on the system.
So M is a collection of M1, M2, M3, M.
Oh yes, I didn't say that. Yes. Oh, sorry, wrong button. So yes, yeah, M is a shorthand for all these bits.
Okay, this translated to open system. So what you have is you have a state on the system, which is your 0 phi or phi tilde, condition of the measurements in the environment, which are all 3 to n, and measurements on the system. The M's refer to everyone or just the
Everyone, yes. So M's,
environment.
we measure both the system and the environment.
Okay.
So M's is everywhere. Yeah.
So like when you sum over M, it means that you choose like a computational basis for M, and then you take every single.
Yes, exactly. So yeah, there's an exponential number of terms in this sum.
So the quantum channel language, when you are averaging, what you have is a channel that takes rho s to some final state of the system.
Yeah. Well, it doesn't take you to a final. It might take you to a final state on the system and ancillars, which is this.
No, but then you're stuck. But you projected the sound over all the emissions in your equation.
So what is written there is something that only acts on the system.
Yes. So yeah, all the operators here only act on the system.
So that gives you a density matrix on the system.
Yeah.
Which is the action of the channel. That's what the channel, quantum channel is.
Yes. Okay. Sure. Yeah. In that case, then
Okay.
this indeed is a channel. Right. So yes, this is just as a reminder. What we're doing, we're taking these row i's, which were the little snapshots that we had, and we're just seeing where they end up on average, and we get this. And what I'm trying to advocate now is have these QMs, consider this as a probability distribution of states. And what we notice is that the actual equation I've written here is actually a degree 2 polynomial of phi tilde m. And what this is actually what's going to actually happen is that these phi tilde m's are going to form a 2 design. That's going to emerge naturally. And if that does indeed happen, then basically we can replace this sum over a discrete probability distribution with the Haar average. And the Haar average is easy to do. So what we end up with is that this row I tends towards something that depends on row S. That's looking good. Okay, why should we really expect this? And this is where my hand-wavy analogies to do with random matrix theory are going to come back in. We think about this, if this unitary is sort of chaotic, then we might expect some form of random matrix theory to apply. And just to kind of give some picture about what that might look like, U is a big matrix, right? And what these unnormalized states here are just small submatrices, and actually they just look like these sort of subcolumns here. So there's one, there's another, and so on and so on. And the point is that each of these kind of subblocks of a massive unitary matrix kind of look random and uncorrelated. And this is a flavor about why we might expect to approach something that looks like the Haar ensemble, namely a quantum state design. Like I say, that's a loose analogy. So yes, Bruno.
But this U will have a state structure, will be, for example,
Yes.
typically local in space, and so.
Right, so we'll get on to spatial structure. Indeed, there's going to be a question about how long do we let the unitary evolve for, and it's not going to be too long. Right? I don't want to be waiting for the age of the universe before we actually approach random matrix theory, but this is just gives you a sense. Let me just check the time. Okay. Good. So let's just for the argument's sake, say that that distribution I showed you does indeed form a state design. So that means that we know on average those snapshots approach this particular state. Well, this is actually very easy to invert, right? We can do it because we have a classical computer representation of this. And then basically this is the inverse that we want to do. So this object equals the target state ρS on average. Good. Assuming that this is a two design, which I will argue for later. Just as a sort of technical point, it's worth noting that this is not a valid density matrix. It's not positive. It does have trace 1, but its eigenvalues can be greater than 1 or less than 0. But as we kind of average more and more, we're going to approach something that looks sensible, we hope. And so if we want to know some arbitrary expectation value, this is what we have to compute, right? We know we have our, this state lives on our classical computer, and we know what expectation value we want to compute is, so let's compute this. And the argument above shows that that will indeed, on average, tend to the expectation value of A. And like I say, we can also do nonlinear functionals if we're interested in that. Okay, and because I'm a little short on time, I've put this slide in for people who know about classical shadows, but I don't want to sort of linger on it too much. So I will briefly skip through this. And then the big question, of course, we wanted to talk about the variance, right? We've got something that on average equals what we're interested in. How many times do we need to do this until we actually get a decent estimate, right? Well, to get the variance, we do similar sort of calculation again. Before I had some expectation value of rho A, of rho I. Here I'm just sort of taking the sample to sample variance of this kind of estimator. And okay, it looks like this. But what we notice again is now what we have, again, using this interpretation of probability distribution of states. This is a polynomial of degree 3, because you can see there's 3 copies of the bra and 3 copies of each ket. And now what I'm going to say is not just the 2 design gets formed, but 3 design also gets formed. And if that does indeed happen, what you can argue, and I didn't want to go through the proof in this talk, but very happy to talk through with people after, is that the variance of this quantity is exactly the same as if we did classical shadow tomography. So that's statistics sorted. And actually, so classical shadow tomography is sort of provably optimal in a kind of in a very specific sense, but we can't really expect to do much better. Okay, questions there? Okay. So just to sum up this part, I said that the dependence of these measurement outcomes on the target state can be captured by this object, which we interpret as a distribution of states. These QMs, and it's a little confusing because obviously there's measurement outcome probabilities and then these kind of more abstract probabilities. They are 2 separate things. But that's the object that we want to look at to understand that dependence. And I argue that that abstract object forms a K design. Well, I didn't argue yet, I told you. And if so, then we know how to kind of backward infer the properties we're interested in from the measurement outcomes. And the variance of those are also should be small. Okay, and yeah, okay, assuming you believe me. The next part of the talk will be trying to convince you that these designs do indeed form, but any questions at this point? Yes.
So just to clarify something in my mind, when you say it forms a K design, I can just think of that as meaning it's a good uniform sampling of the space.
Yes.
Okay.
Yes, actually, I mean, that's a much nicer way to put it. So,
so when you say sufficiently entangling, that feels a little bit like sufficiently uniform sampling of the space.
Yes.
So you're going to be more precise about U?
Yes, I will.
Okay.
I will, indeed, I will put some more stringent constraints on what U has to do in order to. So I just wanted to flash.
You don't have to rewire.
No, I just wanted to just show. So in our case, we're going to have an extremely large number of these arrows, if you like, and that as the number of arrows increases, we're going to cover more. That's going to depend on how many ancillas we put in, how long we evolve for, etc. Yes.
So sorry to insist on this, but let me try to put this, what you're doing in a like a stochastic language.
Okay.
So what a quantum map gives you, if you condition on the measurements, is what one would call a stochastic trajectory. You have an initial state you're trying to infer.
Yeah.
You have some stochastic dynamics that you design, your U, and you look at your sample trajectories, and these are your M's.
Yes.
So then the inference problem you're trying to solve is, given the U that you know, that defines the dynamics, and the trajectories you observe, your M's, you're trying to infer the initial state.
Yes. Yes.
Because you know the zeros, but you don't know the rows. That's what
Exactly. That's exactly what we're doing. I guess I should say, in the spirit of classical shadow tomography, we don't, determining the full density matrix is an exponentially hard problem. There's no getting around that, but certain observables are amenable. Right. So skipped very far back.
So by the way, in some areas, these things like these are called retrodiction.
Okay.
Which is trying to predict measurements on a state in the past from information of the evolution in the future.
Oh, okay. That's an interesting. Yeah. I think we should chat about that. Absolutely. So I've gone the wrong way back. Okay, demonstrating this claim. That's what we've been waiting for. So first of all, there's a few cases where we can make analytical progress. Just to check, Bruno, should I be finishing at sort of 10 to?
But there were many questions.
Okay. All right. I'll sort of keep going. Yes. So there's certain cases where we can analytically have proofs. And actually these proofs are kind of bootlegged off analogous proofs in that field of deep thermalization I talked about. And you can kind of see by comparing what our protocol does to what you do in deep thermalization. So just to remind you, suppose our starting state were U acting on 0. Then what we do in deep thermalization is we measure most of the qubits, leaving some subsystem. And what you can see is basically the part of the circuit here looks exactly the same. So the only difference is in the system, and that we have an input state and we also measure the system. Here we have some predefined state and we look at what the quantum state is afterward. It's the same deal, but we can basically, I mean, for want of a better word, we can steal proofs of people who've considered deep thermalization before. And so this is a bit of a formal statement. First, I'm going to think about situations where there's no spatial structure. That's the easiest to deal with. In that case, suppose U is, and this is where there's quite a lot of confusion about the randomness. So first, we pick a random unitary on the system plus ancillas. And then with that unitary, we go and do the protocol. Right? We don't update the unitary each time. So just want to be clear about that. Then this K-design is formed if we allow ourselves an error, epsilon, and some failure probability, delta. Then this is the scaling we need. So you can see the number of ancillas needs to be sort of scaling with the number of system qubits. And indeed, this maybe answers some questions about what the value of K is. We only care about K equals 3, so let's just take that as order 1. So that's promising. We're kind of heading towards the right thing, but actually engineering a unitary that looks random, even in one of these analog quantum simulators, it's not good. It's going to take a long time. That's bad. And indeed, we'd have to store the entire matrix, which is really not fun. Okay. Then there's a slightly better case. Now, this has some spatial structure. What it doesn't look like is an analog quantum simulator. So, but this is some sort of quantum circuit. We're just trying to add in some spatial structure. And in this case, we can get some analytical power if we look at dual unitary circuits. So this is a case where obviously we're used to unitary gates being having a certain property U dagger U equals I when we go in the sort of time direction. But with dual unitary circuits, we also impose that there's some sort of unitarity in the space direction. I'm not going to spend too long on this because there's some technical details about the proof. But the point is that we actually, interestingly, we find that there's an exact K design is formed in the limit of an infinite number of ancillas when once we reach T larger than the number of system qubits. So that's nice to know. we've added some spatial structure. What might have gone wrong is that we might need to have evolved for an amount of time that is extensive in the system and the ancillas together. You might have thought that, right? Because in some sense, we want to like scramble the entire system together. But interestingly, we only need to sort of, in other words, the light cone only needs to have escaped the system, not the ancillas as well. So that's actually kind of keeping our time nice and short.
But also the measurement protocol has to have some special properties, I guess.
Yes, absolutely. So yes, indeed, you need to be measuring in the correct basis. And in this case, we used, actually, I haven't added the reference here, but from Peter Kleis and Austin Lamacraft's work, they had a particular slight extra demand on the unitaries that form the circuit, which is that they're made up of Hadamard matrices. And then there is a product basis that you can measure in, and this kind of all works. But indeed. Okay, so those are two cases where we can, and I wanted to flag because we have analytical proofs, but really the actual systems that we want to look at in these analog quantum simulators don't really look like this. So in that case, we need to do some, we need to actually look at some representative Hamiltonians. And so we did some numerical studies about this. And for example, we actually fixed, we spent most of our attention on this tilted field Eisen Hamiltonian. So we have nearest neighbor ZZ couplings. We have some transverse field and a longitudinal field. There is some relevance here to loose relevance to Rydberg atom simulators, which actually have a sort of longer range version of this, but also these two terms are present. Yes.
I presume here Z and X are Pauli.
Oh, absolutely. Yes. Sorry, that's unclear. Yeah. So we're in 1D, and the sites are labeled by J. Yes. And for particular, for generic choices of the fields HX and HZ, it's kind of it's kind of agreed that this shows sort of typical quantum chaotic quotes behavior. And in particular, it doesn't have any symmetries. That's going to was one of the caveats that I talked about earlier. And on top of not having any local symmetries, I'm also going to suggest that we break energy conservation. And here my slides are inaccurate. What I should have done is put a big bracket around here and raise power little t. But what I mean is that we're considering Floquet evolution where this generates the dynamics. And we do that to break energy conservation because we want to encourage maximum chaotic behavior.
And H1 and H2 are.
Sorry, H1 and H2. These are different choices of the parameters HX and HZ. We keep this couple fixed. So this is just, it doesn't. The details of this doesn't matter because we expect this generic, but just for sort of completeness, I wanted to add this. And then what we do is we construct that ensemble of states, and what we compute is this so-called trace distance, which in the deep thermalization community is understood that this quantity basically tells you how far away your Kth moments are from the Haar moments. And this is what we get. And it looks nice. So what we have is we're varying the number of ancillas from 4 down to 12. Here I've picked kind of because of the difficulty of simulating quantum dynamics, obviously we can only reach certain sizes. So I've got only 2 qubits in my system, and then from 4 to 12 qubits in my ancilla. And I'm only looking at the K equals 2. Yes.
So sorry, you act on both system and ancilla the same way here.
Yes.
But
exactly.
the ancillas are just prepared in a very specific state.
Yes. Some known state. Yeah.
Okay. So it's not like
Right.
And the system spins, qubits, whatever you want to call them, are in what state? That's
the yes. Okay. I actually haven't. Well, at this point, I'm not simulating the full procedure. What I'm just trying to argue is that design property emerges, and that is agnostic to what state we put in. I will also show plots where we choose a particular initial state and run the protocol. Yes.
That's all right. How would this look if you took an index? So because you're trying to destroy all positive observation plots, right? So
yes.
What if you leave some, for example, you have a transversalizing model and you don't have K, right? So you do have a bunch of observation plots. What would happen to this kind of?
If you do have conservation laws, then, well, basically this is telling you the distance from the full Haar measure. what you would find instead is that you tend towards a different distribution, where basically you are Haar random within each charge block.
Okay, I see.
Yeah, so you have to stay charge diagonal, and then within each block you're fully random. Actually, though, in the case with energy, we're not sure. Energy is a little more tricky. I don't actually have a lot to say about it. Yes.
Really stupid question. I presume here trace distance being 0 would be perfect, and small trace distance is preferable.
Yes, we're looking for a small distance from the Haar ensemble as possible. Yeah. So the lower this goes, the better we're doing. And just to be a little quantitative, what we found, this seems kind of generic behavior, is that the trace distance, as you can see, this is a log scale, decays exponentially with time that we evolve and plateaus at some value that is determined by how many ancillas we have. If you want to understand the value of this plateau, this is basically what you would get is if you sampled 2 to the NA random vectors and then computed the trace distance for that and kind of averaged. And that's kind of, so the number of ancillas is the bottleneck. And you should increase both the time and the number of ancillas until you're sort of, this is kind of the error figure that we're looking for. And that's nice. It decays exponentially with time. Actually, there are some theoretical arguments that suggest it might even be double exponential in time, but we don't really have the width of the range of times in our numerics to really verify whether that's true. But let's just say it's exponential. Okay, so that's an example of what I claimed is sort of typical behavior. We tweak the parameters, we change the Hamiltonian slightly, we still see this behavior. And so that's promising because now we don't need to simulate specific unitaries or Hamiltonians. We just want something generic. And yes, okay. Now I want to put everything together and show you that it all works, because that was some theory about what the formation of designs, but really what we want to do is put this to the test. So what we do is some simulations where we have the system and the ancilla, and we choose a particular state for the system. And just to kind of be representative, we wanted not necessarily just pure states, just to check if there was something special about pure states. So we've got a bell pair state, and like I say, we're a bit limited on how many the system sizes we can reach with our numerics. But if this is some EPR pair 0, 0 plus 1, 1, then some mixture between that EPR pair and a completely dephased version of it. So alpha is some kind of coherence parameter. And we want to measure the fidelity with the EPR pair state. So this is kind of an unusual observable. It doesn't look like our kind of, position operator or single site spin operator. Right? This is the nice thing about what we can do once we have this. And we choose, different choices of the number of ancillas, different time evolutions, and actually in the data I'm about to show, there's also going to be some cases where we also pick the unitaries at random. So we add randomness as well. I mainly talked about choosing a fixed U. You can actually improve performance. All the random unitaries, though, unlike shadow tomography, will just be homogeneous. Just in other words, I'm keeping the constraint on what type of unitaries we're allowed to realize. But I'm just using that to sort of help us converge to the right value. And okay, so if that doesn't make any sense, then just focus on these deterministic principles here, which we measure. And I haven't put the number of ancillas here, which is not very helpful. In each case, we chose the number of ancillas being 9, and then the system will cube it to 2. And so you can see what we're doing is we're estimating the fidelity as a function of different, and we're putting in different density matrices with different coherence parameters. And the dashed line is what we should get if we're exactly right. We've chosen 5,000 repetitions, which seems kind of reasonable with these kind of atomic and optical settings. And so what we have is, this nice linear plot. And I've plotted the error, the sort of the difference between our estimated fidelity and the actual fidelity. These data points are offset just so you can see them all. And yeah, so as we increase, we kind of choose 2 different times. As we increase the time, we get closer to the dashed line, which we're interested in, and like that extra randomness that I said we could add to the protocol also helps. I'm now very much reaching the end of my time. And there were some questions about computational cost, and this is where that we say there's okay, it's all looking very rosy. There's no completely free lunch, but the main demand is, like I said, we had to store these snapshots on a classical computer, and that requires us to do some backwards time evolution. In the previous panel, that was fine because the time that we're actually evolving for is pretty short, and that means we can employ some MPS methods. It's actually the time is the limiting factor, and time that's not a problem. The issue is when we actually really want to study a massive density matrix. We're going to need, if you actually want to reach a 2 design, you need to evolve for very long, and then your classical simulations become hard. But there's a solution, which is what you can do is instead just block up your density matrix into smaller subunits, and then with each subunit, entangle them with a separate set of ancillars. And the point is that each of these will individually reach a design on that sort of sub-block in some order 1 time. And our classical computers are not going to start catching fire. Of course, this means that we don't, it is a slightly different protocol in the sense that now we are kind of scrambling only locally within each block. And so that changes the scaling of the number of repetitions that you have to do. And there's a kind of equivalent problem in classical shadow tomography where you insist on doing local rotations instead of global rotations. But still, this can be well characterized. And what you find is, basically optimal performance in a way that is a precise way meant by this formalism. So that's kind of the only reason we have to do this is because we want to be able to do this in a reasonable amount of time on our classical computers. Good. Right, so that actually brings me to the end of my talk, which, hopefully a paper will be appearing soon. I hope so. Anyway, so our conclusions are we were looking at analog quantum simulators. We introduced a protocol that was going to help us to measure properties of states that we're interested in. And what we wanted is something with the same power as this nice classical shadow tomography technique, without requiring individual sort of site-selective gates and full programmability. And what we did to achieve this is that we leveraged these results from emergent quantum state designs in the community with steep thermalization. And that let us obtain the properties we're interested in. And I showed you a benchmark of performance and showed you that we get reasonable errors. Great, so thank you very much for your attention. I'm happy to take any questions.